Hi everybody, I'm Yuval from AA21, and today we're going to review the latest paper from AA21, the Jamba-1.5 Hybrid Transformer-Mamba Models at Scale, which is essentially the white paper that accompanies the release of the Jamba-1.5 family of models that we just recently had, and it's a continuation of the latest paper from roughly 6 months ago about the new Jamba architecture. Okay, so let's get started. Okay, we're going to review the paper and see the interesting tidbits along the way. And here, this is the paper that presents Jamba 1.5, new instruction-tuned large language models. Okay, this is hybrid Transformer-Mamba and mixture expert architecture, really the first non-transformer-based large language model which is used in production. Okay, high throughput, low memory usage, which is really like the promise of Mamba and the problem with transformers. Okay, so this is what we really try to optimize. We really aimed for speed. And in this case, we wanted to show that we're in the same or better quality as transformers, which is really the state of the art up until now. We have two model sizes, 1.5 large and 1.5 mini, where 94 be active parameters and 12 active parameters, okay, which are roughly in the smaller scale and large size class of models that we have currently in the industry. Okay, and both of them are fine-tuned, and it's very interesting that we released them with 256K token context window, and we're really showing that it is effective context length, meaning that the model can actually use all of its context length effectively, really can understand all the parts in the prompt. And this is really the largest among any open weights models that there is in the market. By the way, if I haven't said that already, these models are open, okay? They're released as open weights, and you can find them here on Hugging Face. Okay, so here we have a link. You can just go download the models, play with them. We also show here a new novel quantization technique called Expert Int 8. This is really just to make our models run on a small amount of GPUs, okay? Really wanted that the main focus here was to make Jamba 1.5 large to work on a machine with 8 GPUs, okay, and process the entire context window that we promise. And really, you can see that Jamba models achieve excellent results while providing high throughput, which is really the goal here. High speed and also maintaining the quality of pure transformers. Okay? And another interesting thing that we will see along the paper is that a lot of the things happen here in-house. Okay? We developed a lot of the things throughout this process, and that really makes it unique and really makes it our own. So let's get started with the introduction, where again, introducing new models, I kind of highlighted the things that seems more interesting. We have some talks about what is Mamba, Transformer, previous works in that. But really, the Jamba, what we call Jamba 1.5 mini, we already released an initial version of it a few months ago, which was already out there with the 12 billion parameters. But here we really take it up to scale. So now there is 94 active parameters out of a total of 398, which is, okay, it's great. It's a lot of parameters. And it's really nice that it can fit into a single machine with 8 gigabytes GPU. It's something which was very hard to do, but still this amount of parameters to fit in this type of machines, and it really works best because this is what we try to optimize it for. Okay, and both of those models that we released are instruction tuned, actually chat models. Okay, so it's not just the base like we released previously. We released both of the chat models as open weights models. And here we also talk about the training throughout, including the instruction tuning. But in particular here, the things that are interesting is that we shine at long context evaluations, both in terms of throughput and in terms of quality, meaning that we actually have effective length of 256K on the ruler benchmark, which we will talk about later on. And 10 times reduction in the KV cache memory, which really, once we introduce the concept of Mamba here, it's not just talking about the total parameters or active parameters. There is another layer of the KV cache that it's going to store in all of that. So we're not only looking at the amount of parameters and active parameters when we're talking about the machines that can run those kind of things. And really, you can see here we have a license for this model that you can just go and read if you want and play with our models on Hugging Face. Okay, we already have like tens of thousands of downloads, especially for the mini. Now, for the model architecture, there's not a lot of new things over here. Okay, so really it's the same architecture as the last one. So let's go to the white paper of the previous one. And this is the version that we released in March. And you can see this is the architecture of the Jamba, what is called joint attention and Mamba. Okay, so it looks something like this. It contains from Jamba blocks, where we have a Mamba layer, and then Mamba MOE, Mamba, Mamba MOE, pure transformer layer, and again Mamba with MOE, Mamba, and Mamba MOE. Okay, I already talked a lot about this type of architecture and will explain how we got that, but really briefly, it happened with a lot of experiments on small scale models, and we found that this version, this type of relations between the amount of Mamba layers, MOE layers, and transformer layers achieves the highest quality with the optimization for speed that can fit on a single GPU. Okay, and you can check out my previous video if you want to learn more about that. And here, so this is essentially the same thing. Now, instead of 4 blocks that we had in the small model, this one has 9 blocks. Okay, so again, massive advantage in the scaling department here. And it's really interesting here, again, to see this table, which is a KV cache. Okay, because what do we have here? Okay, let's talk about it. So we have the available params, which is the total amount of parameters that a model has. Where in transformer, models which are pure transformer, the available params, this is like the total params that will happen. This is all the parameters that both needs to be stored and all the parameters that are taking place when we're doing inference. Now, when we talk about active params, okay, this is something that comes from the MOE architecture. Okay, this means that from the entire parameters of the network, how many parameters actually participate in one inference time. And this is from the MOE. This is something that comes to really help with the speed. Okay, you want low latency for every inference call. And you can see that for models that are pure transformers, these are equal. Okay, so Mistral, the 7B, these are equal. Llama as well. Mistral large is also pure transformer. But you can see that Mixtral, 8x7 and 8x22, these are models that are with mixture of experts. So the total amount of parameters is 47 billion, but the active parameters is roughly 13. And also all the Llama models are pure transformers. And here you can see that the Jamba, because it has the MOE, the mixture of experts architecture part, then we also have this really cool feature that the number of active params is much smaller than the number of available params, okay? Because we are not using all of the network for every inference. And now we also have the KV cache, which is something that also, again, connected to how many hardware do you need in order to inference your model. Where a KV cache, okay, this is like the key value cache. This is something from the attention layers. Okay, this is all the on the cache that you need in order to start throughout the run. So this is something that you need to do on inference time, and you really want it in your cache. It's not something that you can go to the SRAM. And you can see that here, for instance, right? So 7B parameters and 32 gigabyte for a cache. This thing can actually go into one GPU, no problem, with maybe not as long context, but whenever you go and increase the amount of active parameters and also the length of the context, you're getting larger and larger KV cache, which this, like for instance, the Llama 405, something that you cannot really actually fit into reasonable hardware. And you can see here, because we have so little attention layers, pure transformer layers, in our architecture, you can see that the KV cache is very, very small, even with 256K context, which is a lot, right? It's something like 80 books or something like that. So, okay, this is crazy. And this means that you can really fit these type of models into small amount of GPUs, which means that it is cheap and very, very easy to maintain. Okay, also a few things that are worth noticing here is we did a comparison here with Mamba 2. Okay, so what happened is that the original Mamba architecture was released around the end of 2023, okay, which now is called Mamba 1, which we integrated into our Jamba architecture, which we released around March 2024. And soon later, the authors of the original Mamba released Mamba 2, which was supposed to be an improvement of Mamba. And really what we saw here with our experiments towards working on the new Jamba 1.5 large, the larger model, is really to see if it is worth to use Mamba 2. And the interesting thing that we found is that although Mamba 2 is indeed better than Mamba 1 in all of the measurements, really, it's faster, it's improved version, it remains the same quality or higher. But the thing is that when you're using it in a hybrid architecture, in the way that we use Jamba, okay, then there is no upside in using Mamba 2 instead of Mamba 1. And you can really see it here in those graphs, where really the attention with Mamba 1 goes much lower in the training loss than the attention with Mamba 2. So Mamba 2 is indeed better than Mamba 1. We're not saying that it's not, but in the settings of the hybrid architecture, it's actually better to use Mamba 1 rather than Mamba 2. So we do have an efficient architecture, but the model is still very, very large. So let's see all the serving considerations and improvements that we needed to put. Okay, so first of all, we're talking here about what is called expert int8 quantization, which is a new quantization technique that we developed here. Okay, we call it expert int8. This was done mainly in order to really support an efficient serving of the large model. Okay, so it can be fitted into a single machine with 8 GPUs. And what happened here is that if you're just using the whatever out there in the market, we cannot get that. Okay, we cannot really serve this model on a single machine with 8 GPUs. So what we've seen is that over 85% of the model weights are in the MOE layer, and over 90% are in the MOE or MLP layers, which is kind of makes sense. Okay, if we're looking again at the drawing here, okay, so you can see that there's only one transformer layer, and really every MOE layer is essentially a lot of MLPs in parallel. So this is really the majority, right? Because Mamba doesn't have a lot of parameters. It's like that feature of Mamba. That's the quality of it. Okay, so what we want to do is to quantize those weights, but still enjoying the benefits of the BF16 kernels, which are fast and which is commonly used. So what happens is that we quantize the MOE and MLP weights into int8, and then during inference, okay, we dequantize them back into BF16. Okay, and what happens is that instead of just storing all the model and then taking those weights in BF16 to the inference, to the GPU, okay, so to really take it as int8 and then do the dequantization process there, this is something that really saves a lot of time. Okay, and really we put it here, right? So it moves from the GPU to SRAM prior to performing the computation. So the weights move from the HBM to the SRAM when they are in int8, so it takes less time and less memory footprint is cut in half in this case. And really, this is something that happens, okay, really we put it in the FU's MOE kernel in LLM. You can really go here if you want to the vllm GitHub. Here you can see more is the engineer who did that. You can see really the full PR here where he really checks, first of all, different types of benchmarks. So you have the GSM 8K, MMLU, narrative QA, and so on. You can see that with the expert int8 quantization, the quality remains the same. And also you can see that it is faster around a lot of models, not just us. Okay, and really every model that uses MOE can really benefit from that. Okay, so you can see here that the total time of latency really drops down when you are using expert int 8. And so really what happens is that the quantization process has negligible overhead. Okay, that's what we talked about before. It leads to improved latency over BF16 because the transferring of the weights, this is the thing that takes the most amount of time. And just doing the dequantization again from int 8 to BF16, this is like negligible while we cut in half the amount of data that we need to transfer. Okay, so let's review again the advantages, okay, which had quite a lot. Okay, where first of all, it is very, very fast. Okay, this is something that happens at model loading, okay, what we call on the fly. You can really see here the explanation of how to use it. Again, you can use it with any MOE model that you have. Okay, this is something that in the vllm GitHub, here you can just on the fly use it with this flag, so that's cool. Okay, another advantage is that it does not rely on calibration, okay, which can take hours or days and can be unstable. Okay, really, when you're doing calibration, this is something that you kind of want to like find the best points to quantize to, and here it does not do it with calibration. Okay, the weights are really, this is something that is constant throughout the run, and we only quantize the weights and not the activation. So this is why we don't need calibration here. Okay, we can still use the BF16 to hold large activations, which is something which is very, very good. Again, we're not quantizing the activation, just the weights. And this is something which was the big motivation here. It's available to use on A100 GPUs, which are much cheaper than H100. Okay, so again, this is like unlike FP floating point 8. Okay, so this was like the main really motivation to do it. We wanted to make it work on A100 GPU. And really, versus FP8, okay, we're matching in latency, surpassing other quantization technique. We do not lose any quality, and more importantly, we can use it on A100. Here, really, you can see it in graphs, okay, different quantization techniques, and really on H100, expert int matches the latency of FP8, which is great, and on A100, FP8 is unavailable. So again, no reason to use other methods here because this really shows no loss of quality. It works really, really well on A100 and also on H100. So this is a new quantization technique that really helps us to serve our model on one machine with 8 GPU, 80 gigabyte GPUs. Also, another things we added here is the activation loss, which in general, right, when the larger the model is, the larger the activations can go because it goes through a lot of layers. And really, most of the activation, okay, so we say here specifically the output of specific experts and the output of the last Mamba layers are gradually increasing in magnitude. Okay, it's something that happens a lot in a lot of especially large or deep networks. Okay, but here we're talking about values of like, okay, this is 4 million, which is a lot. And though it does not hurt the actual pre-training, okay, because we're using their BF16, okay, this is something that is problematic mostly for the inference, okay? It can cause numerical issues during this inference. So that was the problem that we noticed, and really to come and help with that, we added something which is called an activation loss term. Essentially, this is like a regularization term, okay? And so it's proportional to the mean square of the activation in every forward pass. And you have here like the alpha factor, and you can really play with it. And the point here is to penalize larger activations. Okay, and really we've noticed that when we use that for the training of Jamba-1.5 large, okay, it was enough to reduce the activation to something like up until 3K instead of what we had before, which was millions. Okay, where this is something which is really, really nice. It kind of makes sense, right? It's not like the most original thing to do, but it is important to do it here. And also we noticed that adding it to the loss, it reduced activations almost instantly, meaning that we can put it at the end of the training process instead of putting it all from the beginning. which is nice because every time you're adding another term to your loss, right, you're kind of getting forcing the model to learn another thing, which we really didn't want the model to focus on something other than on the data of the pre-training. So once we can get the model to really work well with all the pre-training data, and really in the end just adding this loss, we really lowering all the activation values by still not hurting the training process, which is great. And you can see here, okay, just a note, full evaluation suite on the model with the FP16 activations, and we got roughly the same results. So that's nice. And here on number 4, we're talking about the throughput and latency analysis, which again, this is where this architecture really shines. Okay, this architecture comes to help with high throughput and low latency. Okay, this is where the reason to use something which is not pure transformers. Okay, and you can see here that really our models obtain much better latency and throughput than similarly sized models and really shine at long context, right? And why does this happen? So the transformers, because of the way it's built, they have this this quadratic time complexity because for every token in the input, I have a matrix that says how it communicates, how it relates to every other token in the input. Where in Mamba, it's kind of linearly goes. So this is something which we really expect, and as always in complexity, right, the longer the input, the bigger the input, the bigger is the difference when we are measuring those type of things. So you can see here for Jamba-1.5 mini end-to-end latency, really on 4K, 8K, 16K, and so on, where we are doing all of these on the same hardware. Okay, I think it's also, let's see, they're saying here. So what you're seeing in these experiments, we're using two A180 gigabyte GPUs. Okay, and you can see here that really on smaller contexts, it's roughly the same from Llama, Mixtral, and Nemo. But when we are going a bit higher with the context, you can see really a significant difference here with 256, 128. Okay, so this is really something that you're seeing, that the longer the context is, the higher the difference. And also again with the throughput, okay, so you can see here that while all the others, which are transformer based, really decline somewhat quadratically with the amount of context, you can see that the throughput for the Jamba architecture remains roughly the same. It goes down a little bit, which makes sense, but not in a quadratic way, not in a meaningful way. And you can see it again over here with large, where here instead of 2 A100 GPUs, it runs on 8 A100 GPUs, which again, only feasible because of the expert int quantization technique. Okay, and you can see here versus Llama 3.170B, Mistral Large 2, and Llama 3.1 405, which you can see that the big Llama, we can't even run it on those type of on those contexts with these machines. You can see here really the gap seems significant, and also here again with the throughput. So all of them go down roughly the same. Well, the Llama one really takes a dive, but really you can see that the architecture of Jamba makes the throughput to be better start from the beginning. Okay, and it really remains somewhat constant throughout the length of the context. So now let's talk about the training. Okay, so first of all, we have like the more dry stuff maybe. So we're training it on an H100 GPU, in-house proprietary framework, some expert parallelism, mega blocks, and so on. And really, it's more interesting, I think, to look at the stages of the training and try to understand what happens in every stage. Okay, so we're saying roughly dividing it to 3 stages, which is a pre-training, mid-training, and post-training, where somehow with all those words, like there's not a single stage which is called just training. You're either pre, mid, or post. The entire process is the training. So the pre-training is where we train on in-house dataset. This is something that was last updated on March 2024. So this is the knowledge cutoff. Okay, and you can see here this a mixture of publicly available data with in-house data. Really, we have a pre-processing pipeline, which includes a parser, which we developed here, quality filters, deduplication, and so on. And really, we developed the in-house parser that is something that really gets the most out of every document, which was something that was invested a lot of work on here. But in the end, okay, the exact data was a mixture of the data that came from different parsers. The massive majority came from our parser, but still we found that there are other publicly available parsers that can maybe are experts in certain domain that we want to take it from there. Okay, so also important to say here, this stage included multilingual data, so English, Spanish, French, Portuguese, Italian, Dutch, German, Arabic, and Hebrew. And spoiler alert, we found that it actually performed really well just based solely on those, to include these languages in this phase of the training. Okay. After the pre-training, we did something which we called mid-training, okay, a short phase of it, which is something that we really put a lot of emphasis of utilizing long context. So we put a lot of high proportion long documents. Okay, this is something we really want, long context capabilities. And so this was the main focus in the mid-training. And after that, the model is called trained, and now we're moving to what is called the post-training, or sometimes called the SFT, okay, the supervised fine-tuning. That's where we are right now. And this is something that we really want to, A, give the model various skills and conversational abilities, but B, also retain the capabilities from the pre-training, especially the long context one. So really, we want to show the model, this is what we expect you to do with all the skills that you need to learn, but we don't want it to forget and really hurt everything that happened so far, which is a problem that often happens when you are fine-tuning a model to something. Okay, so, and again, this is objectives that are partially conflicting, something that is well known, it happens a lot, right? It's like there's no free lunches. There are also works that show that if you take a model and you make it better at understanding instructions, it loses maybe some sort of creativity, other things. So this is something that we really wanted to strike the perfect balance between them. Okay, and really what we did here is we wanted to do a supervised fine-tuning, sorry, with high-quality conversational data, skill-specific data, and long context data. These were like the important things here. And what we did is really use a lot of synthetic data, right? We want to train the model on a lot of data, and this is currently the best way to do it. And really, a lot of foundation models recently have done it as well. And we developed like a pipeline for generating synthetic data in-house, which are in the same, like the following pattern, which is roughly common up to some changes. So first of all, we're sampling or generating prompts from target distribution, then generating response from language models, filter or ranking them and quality according to automatic validation and scoring. Okay, so just ditch the ones that we don't want, and then post edits to remove artifacts and fit the desired prompt. Okay, so these are the stages. Again, this is something which is quite common from the first Alpaca paper, I think, that they talked about how to generate more synthetic data. It follows through the same guidelines with some improvements. And really, we have several notable examples of the synthetic data generation. So that table-based QA, okay, so we really wanted the model to be good at tabular data. And really, we have generate training examples that include extraction, aggregation, and attribution tasks. And you can really see here a link to a workshop where we explain much more on this type of table-based understanding. Document Q&A, okay, so we really want to prompt for the model to really understand how to answer grounded questions. Okay, grounded meaning that it's only answers based on the context it's provided, and both single and multiple paragraphs, meaning that we wanted to succeed in like the needle in the haystack part, but also in like multi-hop questions. And again, we sometimes embed these examples within longer contexts, just to really give the model better grasp of handling long contexts. Okay. Tool use, okay, so this is something which is quite standard. Okay, we really wanted the model to, as part of like the world going to the agents part. Okay, so we want the model to really understand when it needs to use external tools. Okay, nothing too extravagant here. And steerability. Okay, so this is something which is more interesting, I think, in the development process, where a lot of the definitions that we had in mind for the model is to have the skills or to have some sort of measurements that you can easily validate and synthesize those prompts. And this is something that really helped when, sorry, when we wanted the model to learn better or really tune it towards desirable properties. So some observations that we got from that is that, first of all, like I spoiled before, we only included a small fraction of non-English data in the post-training, but Jamba 1.5 models really perform well in multiple languages, specifically in the MMLU, the benchmark. So really, probably the fact that we do not include it in the post-training process, but we do include it in the pre-training phase, that's probably what makes it be much better in the languages. Okay, so it really doesn't have, you don't really have to invest a lot of time in multilingual in the post-training if you're doing it right in the pre-training. Also, because of the architecture, that it's really efficient in long context, the interesting part for us as developers here is that really for the same budget that we have for fine-tuning, we can do a lot more experiments than on pure transformers. So this is something which is really good if you're just taking the model from Hugging Face and you want to test the best parameters or like really understand the best way to fine-tune, you can really experiment with that a lot and still maintain the same budget that you originally had. And first of all, and lastly, there's a lot of talk right now about PPO, DPO, and like reinforcement learning. And these models are only went through SFT. Okay, and we find a combination of careful synthetic data generation, data filtering, and supervised fine-tuning is crucial for obtaining a strong post-trained model. Okay, so we're not even coming to talk about like the RL here or yes or no, but just the importance of really making sure that data, the data generation and filtering is something which is really, really important for fine-tuning and something that will provide you a really, really powerful fine-tuned model, even if you're not doing reinforcement learning as part of the process. And then lastly, we have the evaluation part, which is something that every paper has. Okay, and here we have three types of evaluations. So we have academic benchmarks, chatbot benchmarks, and long context evaluations. Okay, and really all these papers, since our models are open weights, okay, so we really compare with all the open weight models that we have in the market. So there's the Llama and Mistral version, and also Gem. So for the academic benchmarks, again, not something that will maybe wow you, a lot of common benchmarks, okay, where all the numbers here are either something that we ran or taking from official sources. Okay, so you can see here on pink our models. So we have the MMLU, MMLU Pro, and so on. You can really see that Jamba 1.5 mini and large both are comparable, either better or slightly worse, but really comparable with all these pure transformer models, which is right, something that is great, right? Because they are faster models, more efficient in memory, and comparable in the quality. So that's what we aim for. This is something good. The chatbot evaluations, this is something that we use both Arena Hard and Wildbench leaderboards. And by the way, you can also see us in the chatbot arena right now. Both of our models there. You can play with them. You can rate them if you want. And this is what we're showing here is the Arena Hard benchmark, which is an automatic benchmark with LLM as a judge, which is a good proxy for the chatbot arena. And Wildbench, again, a leaderboard which uses GPT-4 as a judge by AI2. And you can see here that this is the Arena Hard, we are getting really, really strong results. And also in Wildbench, we are very comparable with all the other models. And long context evaluation, okay, so this is something that is really something we focused on. because we do believe that long context is something which is prominent to the industry and something that businesses really need. Okay, so we have our models with 256K context window, and we want to show that it's actually effective. It's not just a physical property of the model. So like in the previous paper, we used the ruler benchmark to show that this is effective benchmark. This is effective context window. Okay, so this is a benchmark, something that was released by NVIDIA several months ago, which is a set of 13 synthetic tasks. Okay, some of them are like a needle in a haystack retrieval tasks, which is if you have a lot of text in the context, and the information that you need is somewhere there. Okay, so like finding a needle in a haystack. And also some of the tasks include multiple needles, so you have to like take them from different places. Tracking task where a chain of variable bridging should be returned, aggregation tasks, and 2 question answering tasks. Okay, so this is like, though it's synthetic, it's something which really represents tasks that require the model to either find something in long context or take several things and really connect them into the answer. And you can see here that both Jamba 1.5 mini and large are the only ones with the confirmed effective length of 256K tokens. Okay, so you can really see here, even though Gemini, for instance, had a bigger claimed length, we actually didn't manage to reproduce this result for 128K even, but we still gave them the benefit of the doubt because it was published. Probably, right, this is something that was published in the main GitHub, but a new version was released of Gemini, so probably in that version they kind of hurt the long context capabilities in order to improve other things. Again, no free lunches in life. But you can see here really that we, in the Jamba models, maintain high scores in the effective context length window. Also, you can see infinite bench, which is really a collection of data sets that really has like average length of 100K tokens. The really long context examples. And we focused on 2 of them. So 2 English tasks, so question answering and multiple choice question answering. And you can really see here that when we are compared against Llama 3, so we're really off the charts here. Gemma 2, we can't even run it because it has a very short context window of 8K, and also the large one, really getting really good results. And again, in multilingual capabilities, so like we mentioned before, the multilingual MMLU, we're seeing here good results across the board, very comparable with other models that we have. So just a few quick things to wrap up the video. So we have here the alignment and safety considerations, where again, you can read all about it. Our models are default business code of conduct based on our participation in industry standard bodies, think tanks, and direct experience with our customers. Okay, we have a lot of details here about the OECD that we are in the task force. And you can read about it. You can also see our trust center in our website if these things are more interest to you. But really, this is something that we put emphasis on because we do believe it's important, and we do see that it's something that enterprises really need. Okay? The concept of being safe to do not be harmful in the prompts. Okay? So this is something that is really reliable for enterprises and something that we really put emphasis on it. So in conclusion, okay, all this paper is a Jamba 1.5 large and Jamba 5 mini introduction. Okay, really the first non-transformer model in the market. This is a hybrid Mamba and transformer with mixture experts architecture, really aiming for speed here. Okay, this is the thing. We really wanted speed, we wanted low memory, and we wanted to show that we can match the quality of others. So I hope that you like this. If you want to learn more about the Jamba architecture, you can check out the previous video, and thank you.